Hello, welcome back to our isometric game. Let's see where we left off last time. So last time we implemented movement range. So there's a limited range any unit can move. But they all have the same limited range currently. And one of the major things in these types of games is that movement and positioning is very important. So I think it's very important to differentiate the way various units can move. So some might have a bigger range than others. And let's try and start implementing that. So first I'm going into my action test and I want to implement range differences first. So let's write a new test. Okay, so we have a flat map. Then we assert that if we create a move action reachable tiles in this map for the short range entity, we get back less tiles than for the if we create a move action for the long range entity. So let's run the test. And the test fails because they still have the same range. We are never setting a range anywhere. So let's implement that. So let's go into our entity and make sure that our entity has an actual range. Meaning that we need to initialize it, and what we'll do is this. To not break what we already have, we'll create an initializer with the default value of a range of 3. Now we also need to use this one, so let's go into our action, into our move action, and somewhere here we're using a hard-coded range value. Time to get rid of this one. We can use our entities range. And if we now now run tests, the test should pass. And the test still fails because, of course, I forgot to give them both a different range. So let's try again. And now the test passes. If you want to see in the game itself, what we can do is we can go into our content view and, for instance, give our rogue a bigger range than our knight. So let's see, our knight can move 3 tiles, for instance, to the front, and the rogue can move 4. So the rogue has a larger range. So that's how far you can move. What I also want to do is I want to limit how high an entity can climb or jump, and I want to differentiate that. So for instance, imagine this a knight with its bulky armor probably shouldn't be able to directly jump on such a high cliff, and in this case it can't because of the range, and the difference is also taken into range when calculating the cost compared to range. But if we didn't do anything like that, the knight could simply jump directly here, for instance, if we gave it a bigger range. Whereas, for instance, a flying unit might be able to traverse any height difference as long as it's within range. So that's, we want to basically, we're going to differentiate units by how far they can move and how much elevation they can traverse. And this is a bit A bit more work because we don't take this into account yet anywhere. The first step will be creating different Dijkstra maps. So let's take for instance this height map we have here. If we have a height map that create a Dijkstra map that takes a maximum height difference into account, sometimes you need to take a sort of long way round to get to a certain position. The A's here stand for tens. So let's first make sure that our Dijkstra takes the max height difference into account. So let's go into our map test and create a new test. Dijkstra takes maximum height difference into account. So we need a map, and we can use the example height map. Then we create a Dijkstra map. The target can be 0, and we have an expected result, and that will be this. So we can fortunately copy paste from ASCII flow and put it in, although I need to change the A's to tens. Then we need to check for every row and every column in every row that what we get back in the expected result is the same as what we find in our Dijkstra map. X and Y should be the same as expected result Y and X, because that's an array and the other one is a dictionary. So let's run the test. And the test fails because we're not doing yet anything with height difference. So let's open map side by side, and let's see where we create a Dijkstra map. We need to take height difference into account. So let's see, so we have a target here. Let's also add a max height difference that we can pass in, and by default this will be basically unlimited, so the maximum integer value. Now we need to use this somewhere while finding our neighbors, and our neighbors also need to take the max height difference into account. So this way, when we get the neighbors for the current node, we can also pass in the max height difference. But we're not yet using the max height difference in the getNeighbors function. What I'll do is I'll create a new function called entroball. And this is a helper function that says if we can go from a specific point to a specific point with a max height difference, we return a bool whether that is possible or not. We need to get the neighbor's height. This will be our from position, and we have to get the node height. That's our to position. If we can't, then there's definitely no pop, so we'll return false. Otherwise we return the difference between neighbor height and node height and see whether that is at most the max height difference. So if it's more than the max height difference, then we can't enter. And then we can use this function in the getNeighbors4 function. We're filtering here on tiles that contain on valid tiles, and then we also need to filter on enterable. We go from any tile to a specific node with the specific max height difference that was passed in. So now we can use max height difference. Let's see if we can add that to our test. So let's go back to our map test and make sure that when we're creating our Dijkstra map, we're passing in a max height difference of 1. And let's build and run, or at least let's run the test. And now the test passes. So we're able to create Dijkstra maps that take a max difference into account. So that's cool. Now let's see if we can also get the paths to take the max height difference into account. So when we create a path based on the Dijkstra map, we would want to make sure that it also takes the max height difference into account. So let's create a map, and in this case we again need a very specific map. Let's show it here. So when we create a path, for instance for this map, we can't go from here to there directly or from here to there directly. We basically need to go the long way round. In the old way we could do a sort of, if there's unlimited maximum height difference, then you can sort of go directly. Otherwise you need to go the long way around. So let's see. So this is, we can fortunately copy this map, at least to an extent. Add some of these. So we now have a map. We create a Dijkstra map. From the 0 position, let's choose a max height difference of 2. Then we need to get a path. Let's say we go to the vector 2 by 1 using this Dijkstra map. And then we get an expected path back. And that one contains a couple of vector 2Ds. This is a bit tiresome, but that didn't go as well as I hoped. So we start at 0, 0, then we go to 0, 1, then we go to 0, 2, so we're moving downwards. Then we go to the right, again to the right, again to the right, then we go up, and then to the left. So we're really taking the long route, and we assert that the path we get back is the same as the expected path. So let's run this test. And the test fails because we get the short path back, and that's reasonable because we're not doing anything with a maximum height difference yet. So let's add that to our path. So we have a used Dijkstra map. Let's also add in a max height difference, an integer, and again we can default it to int max. Let's see, so we can choose We can now pass in a max height difference. 2. Now the test still fails because we're not yet using it. And we need to use, the problem is that having the Dijkstra map alone isn't enough. Because our algorithm of calculating the path simply takes the Dijkstra map. The Dijkstra map takes the height difference into account, but the path simply starts at the end and chooses the lowest neighbor it can find. And in this case, that would mean that it simply tries to take, it goes directly from the highest point, for instance, to this one, because it's the lowest one it can find. So it will lead to the shortest path. Here again, we need to choose the lowest one that also is within the maximum height difference. So it needs to go first to this one. So we can't just use the minimum. We need to do this a bit different. So we have our neighbors. Then we can choose a new current. This will be the neighbors. And we filter on whether they are enterable. And then we can pass in the max height difference. So this filters out all the neighbors that are not valid. And then we choose the then we can get the minimum. And then we have a new current, so we can say that current is new current, and then append it to the path. So let's see if this now works correctly. So the test still fails, and let's see where this goes wrong. It does look kind of the same. I'm going to the right position. Oh, we have made a typo here. Okay, so I want to do one final test here, and that's the situation that we have a height difference that is so big that you can't reach the target position. So it's sort of like you're reaching a wall or a steep cliff. In this case, I want to get path return an empty path if the height difference is more than max. So we take our map. And we will construct a specific map for this case. So it will be a small map, but it will have a big, steep pillar in the middle, somewhere in the middle. We make a Dijkstra map. And we create a path. And let's see, we want to reach that high point, so that's at 2, 2, using the Dijkstra map with a max height difference of, for instance, 4. And then we want to assert that our path equals to an empty array. So let's run the test. And now our test doesn't specifically fail, it even completely crashes the app, because we're now doing a force unwrap of this new current variable where it is possible that no valid neighbors exist. And then this optional gets returned, it will be nil, and we're force unwrapping it. So we need to be a bit more careful. What we can do is this. in the case that we get, let's get rid of this one first. Let's say if let new current. So if we find a new current, then we can set current to new current, else there's no valid neighbors, meaning there's no path. We can simply return the empty array. And now if we run the test again, it pass. So, okay, cool. Let's continue. So now our map is aware of maximum height differences. We should start using them within the actions as well. So let's go into our action test and create a test that uses the reachable tile. So we create a test for MoveAction. Reachable tiles takes a maximum height difference into account. So we need an entity. So let's give the name as a start position. It has a range. Let's give it an unlimited range for now. Then we create reachable tiles. Is a move action that reachable tiles in a map. And let's create a specific map for this one that is quite small. And it will be for our entity. So the case we are creating is this one. Basically, this is the map we're creating with a larger of a higher point in the middle. If we have a max height difference of 0, of 1, then we can't reach the middle one. So the returned reachable tiles will be the ones around, but not the one in the middle. Okay, so we have our reachable tiles. Then we have our expected reachable tiles. And this will be a set of vector 3Ds, 0, 0, 1. There will be 8, because we're missing the middle one. So this one, the middle row, and the bottom row. We assert that reachable tiles.count is the same as the expected tiles.count, and also we go through each reachable tile in reachable tiles and assert that expected reachable tiles contains this reachable tile. Let's run the test. And the test passes because we get back the entire map instead of only the 8. And that's because our entity doesn't take, we don't take max height difference into account when creating the our action yet. So let's go into our action. And we also don't take we would like to do something like, we're creating the diagram map here. We want to do something like max height difference, and that would need an entity to have a max height difference, but the entity doesn't have one yet. So let's go into our entity and add that one. And we'll default it to a very high value. That way our current test won't fail, and I think if we run the test again, it should now pass. let's see, it's not, oh, that's because we also need to pass in the max height difference for the entity in here. Let's try again. And now the test passes. We're nearly there. There is one specific case that, well, let's try and use this one for first and see what happens. So let's close this one. Let's go into our content view and let's add some max height differences. So this one has a bigger range. Let's see, and let's say that our knight have a max height difference of 1. And let's run. So when we move, we see this one can't move up here, even if we go here. We move, even if it's really close, it can't go up here because the maximum height difference is too big. And the same applies to this one. However, let's see, let's get this rogue a bit into range. The rogue indeed is able to reach this position. There is one bug still though, and it's a bit difficult to show in the game, but we can show it in a test. And that is that the move action itself, when making, doesn't take the height difference into account yet. So what we want is that also make takes a maximum height difference into account. So we need an entity. And it can start from 0. It will have an unlimited range because we're not interested in range now, but it has a max height difference of 1. Let's create a move action in this map for this entity. And we want to go to 2, 1, 3. Then we expect a path that's taking the long way round, and we assert that the move action path is, the move action is an optional. Let's make this a throwing function, and we can use a rep to make sure that we get back this needs to be the example map. Then we can do move action path, and that this is indeed the expected path. So let's build a run, or run the test at least, and the test fails because we get the short path back instead of the long way round. So to solve this, what we need to do is we need to go into our action, and here in our make function we simply need to pass in the max height difference of the entity, and the same for the path. And now if we run the test, this should pass. Okay, so to wrap up, we now have entities that we can differentiate in terms of how far they can move and in terms of the height differences that they can traverse. So for instance, this one can't go here because it's simply also the difference is too big. Otherwise it should be able to do so. So I think that's we're almost there when it comes to movement and positioning. There is one thing I want to do next time yet, and then I promise we will be done with movement at least for some time. And no promises that it won't go back, but I want to make sure that there's only 1 unit per tile. So for instance, our knight, let's take the rope, it moves a bit faster, can now also go to a place where the knight already is standing, and this is not what I want. So I want to limit to 1 unit per tile, and after that we can start working on actually attacking and make this into a proper game. So thanks for watching and have a great day.